Unit 9, Lesson 2, Part 2, Geometric Functions. Geometric functions are circular functions which relate to the angle of a right-angled triangle to the ratios of two sides. There are three primary functions, and many of you have seen these before. You may have heard of the acronym SOHCAHTOA, and that relates to sine, cosine, and tangent. Now, we don't say the words sin, cos, and tan. Again, this is just going to be an abbreviation for sine, cosine, and tangent. Now, there are three secondary functions that are the reciprocal of the primary functions. That would be cosecant, secant, and cotangent. And these are the acronyms we use to represent these secondary or reciprocal trigonometric functions. Today we're going to talk specifically about sine and also introduce cosine functions. Both sine and cosine, until you dive deeper into them, will look very similar. They make this ongoing wave shape. Now, how do we graph one basic rotation? Remembering that trigonometric functions are circular functions. So let's look at the unit circle. As we learned in lesson 1, we're going to start right here. And I'm just going to divide this 1 unit circle into 4 equal parts. Each one of these, by the way, is referred to not as a section, but as a sector. So when we start here, and I had to come up with an ordered pair, this ordered pair would be go to the right one and then stay to get to this point. Now up here at this point, we're going to go by staying and then moving up 1. Moving to the left 1 and staying, and then down below is going to be stay and drop down 1. And that just relates to your ability to graph ordered pairs on a Cartesian plane. When we look at these ordered pairs and we relate it to a trigonometric graph, I want you to know that although we think of this as x, y, the first value is the cosine and the second value is the sine. So let's get started with doing a general graph of a sine curve. So when we're here, right here at the very beginning, let's look at the value of the sine because we're graphing the sine. The sine is 0. So I'm going to go and make a dot. Okay, now I'm going to divide again this unit circle into 4 pieces. So I'm going to do 1 step. And we've already talked about this. So in unit 9, lesson 1, we talked about how this can be seen as 90 degrees or it can be seen as 1 pi over 2, right? So when I get up to this a 90-degree mark at this point, and I can write 90 degrees, but really in math, we're going to drop that into radians most often. Now at this point, the sine value is 1, so I'm going to go up 1. And now I'm going to go to the second sector, which would be 180 degrees, also known as simply pi, and my sine value is 0. Then I'm going to drop down to 270, also known as 3 pi over 2, and my sine value is -1. And coming back to complete this revolution at 360, so at 360, or 2 pi, I am back to a sine value of 0. And so when I connect these, we're making this shape that is a wave-like. So it's not going to make what looks like a V at the end, a sharp point. It's going to be this wave. It reaches a high point and then a low point. Now this is a continuous curve. As you go to the left and to the right, it's going to make that general shape for a. Let's take the same concept that we used to graph the function y equals the sine of x, and now relate it to graphing the function y equals the cosine of x. So we're going to use this unit circle again, remembering that trigonometric functions are circular functions. So let's start at 0. At 0, the cosine value is 1. So my output of the function is 1. Okay, going up to 90 degrees, also known as pi over 2, my cosine value is 0. The output value is 0. At 180 degrees, also known as pi, the cosine value is -1. That's the output. And back to down below to 270 or 3 pi over 2, the cosine value is 0. and completing the 1 revolution back up to top here, we have a cosine value of 1. So it would be common for us to think that we're going to make this V shape, but remember that both sine and cosine values make a wave shape similar to this. So, and it's ongoing to the left and to the right. And what I mean by that, when I show you this, it'll be visible in the 4 graphs below. So this is 1 revolution of a sine function and 1 revolution of a cosine function. They are the parent functions for both sine and cosine. Let's now describe what happens when we change, we keep the basic shape, but we change how this looks. So we either elongate it or we compress it, which means there's going to be multiple, if I could do this a little bit better, I should have done this in advance, but there's going to be multiple of these wavelengths in a shorter period of time. Oh, that was a bad example, but you get the general idea, right? So do we elongate this or do we compress it? And so let's first start by looking at this sine function. And so I plugged it into Desmos so we can see this, and it relates to what we just did. So we can see our output is 0. Then we go to our first step, which is at 90 degrees, right? There's 90 degrees, and I went up 1. We go to our second step, which was at 180 degrees, which is 1 pi, and our output is 0. Our third step is at 270 degrees, our output is -1, and our fourth step is at 360 degrees, 2 pi, and our output is 0. Now look, if I take this and I move this, we can see this is an ongoing periodic function. So that wave continues at that exact same rate. Let's talk about a few terms here that really matter. We have a line here, and I'm going to come over here and I'm just going to type in y equals 0, and I'm going to make that into a dotted line. So I want you to recognize that this is the midpoint of this periodic chart. I guess I don't know how to make that into a dotted line, so we'll save it just like that. And so the distance to the highest point above or the lowest point will always be the same. So from here all the way up is a distance of 1, and from here all the way down, well, we could say is a distance of -1, but remember, distances are always positive. So it's a distance of 1 above or below the midpoint, and that distance is referred to as the amplitude. Again, the amplitude is going to describe how far above or below the midline does our function move. Now, 1 cycle here is referred to as a period length. So our parent function, y equals the sine of x, has a period length of 2 pi. Again, that means it takes, if I look just right there at just our period, it takes a length of 2 pi to do 1 cycle. Now let's change this up and let's look what happens. If I change this, and let's make it drastic, let's do 1 over 10. Whoa. Okay, if I do 1 over 10, we can now see that if I take this out for just 1 second, we can see how long it takes for 1 period length. So here's up to the highest point. There's our highest point, still has an amplitude of 1 to the lowest point, but we can see instead of it taking 2 pi, it takes 20 pi to complete 1 cycle or 1 period length for this particular function. Now what if we change that to 1/2? And what if we compare it to our original parent function, which was, let me take this and copy and paste it, and we're just going to make this into the parent function right there. Let's go move in here. So the parent function we had, our general parent function that we can see it right now is in purple. Again, we can see it goes up, amplitude 1, and there it meets right at that point, right? So it takes 2 pi for our parent function to complete the cycle. But what we see in green, how long does it take? So it starts here, amplitude is 1, we can see that, comes down, but it takes 4 pi. It takes double the amount of time. And so we're going to learn without graphing it, how can we determine how long, based on an equation that's presented to us, how long will it take for 1 cycle or 1 revolution to graph? So here's the elongated function. It may look very similar to here, but notice that I was able to do over the hill and back to this midline in pi, and down here I had to double the amount of time. So over the hill and back here it took 2 pi. Again, it took 2 pi to do 1 cycle, and here it takes double the time, which is 4 pi. And this is the equation example y equals the sine of 1/2 x. So we've talked about elongating a function or a period, but what if we compress it? So this is our general function, and what if instead of having a 1/2 in front, I put a 2 in front? So a period or period length is the interval over which the function completes one full cycle before it starts to repeat. So here we can see we have a hill and then a valley, and we've just finished one cycle before it starts to repeat. So the function that we're looking at in green takes a length of pi in order to complete one cycle, versus the function we see in purple that takes a length of 2 pi. It takes double the amount of time. So I actually drew this graph here, and this was y equals the sine of 2x. So this is elongated. If we compare it to the parent function, the period here and the period length here is compressed. Now, how could we actually identify the length of one cycle before it repeats without having to graph it? There is a way. And the formula is, let me first have you write down the general formula for a sine function. So y equals a sine of bx minus c plus d. Now we're going to get into more of that in the next 2 chapters, but in this lesson and the preceding lesson, we're going to focus on amplitude and the length of the period. So we're going to simplify it, and again, in Unit 10, it will get a little more complicated. All right, so how can we determine the length of the period? There's a simple equation. We're going to take 2 pi and we're going to divide it by the b term. The b term we can see is going to be the value directly in front of the x. So in this example, the value in front is 1/2. So I can figure out the length of the period by taking, in this case, 2 pi, and I'm going to divide it by 1/2. And when we divide by a fraction, we're going to multiply by the reciprocal. So 2 pi over 1 times the reciprocal, or the second value is going to be the reciprocal. So I flip 1 over 2 to 2 over 1, and I end up with 4 pi. And look, it takes an interval length of 4 pi to complete one cycle before it repeats. Let's look at our second example in which we compress the period. I'm going to take 2 pi and I'm going to divide it by the value in front. The b value in front of the x is a 2. Dividing it by 2. Here I don't have to write it out in a horizontal form because the number underneath is not a fraction. The 2's are going to be simplified, and I'm left with just pi. That means one cycle, the length of one cycle for the function to complete one cycle before it's going to begin to repeat. Okay, next let's talk about amplitude. Let's look at the 2 graphs down below and let's compare them to what we have up above. So I'm looking simply at a sine function here, and the amplitude, by the way, amplitude here is the a value. And if we're given an equation, we're going to take the absolute value of this. Why? Because we know amplitude is going to describe the distance from the midline up to the highest or lowest point of the function. So here we have amplitude of 1. I can see that on a graph. Let's go down below here. Down below, I can see that I have an amplitude of 3. Why? Because the distance from the midline to the highest or lowest point is a distance of 3. In my last graph, I have an amplitude of 0.5 because the distance from the highest to the lowest point of the midline is 0.5. Amplitude is always going to be positive. It is the absolute value of the a, which always is going to be stuck to the sine and directly in front of it.